Hello everyone, my name is Saksham Purve and this is my lab report for black holes. The overall purpose of this lab is to find the initial velocity of our ship so that it can fly around the black hole without crashing. In order to do so, however, we first must calculate the mass of the black hole. In this lab, we will be building two computational models using VPython and GlowScript. The fundamental principles involved in this lab are as follows. We begin by describing the momentum principle, which states that the net force is equivalent to the change in momentum over time. The net force, which can be calculated by summing the parallel and the perpendicular components of force acting on the object. The position update formula, which states that the final position is equivalent to the initial position plus the average velocity times delta t. The velocity update formula, which states that the final velocity is the sum of the initial velocity plus the F net over m times delta t. In this lab, we'll be studying the gravitational force of fundamental force interaction caused by the attraction of large masses, which can be calculated by g m1 m2 over r squared, where g is the gravitational constant and r is the distance between these two objects. As seen here, every force has a parallel and a perpendicular component, and that the gravitational force is inversely proportional to r squared. In this experiment, our system is described as the star in part 1 and the spaceship in part 2. In both parts, however, the surroundings is the black hole. We will first edit the computational model in part 1 to obtain the mass of the black hole, and using the mass, we'll use fundamental principles to calculate the initial velocity needed to escape the black hole. Overall, we conclude the average mass of the black hole to be 1.22 times 10 to the 34 kilograms, the net force to be 9.77 times 10 to the 28 newtons, the parallel component of the force to be 4.37 times 10 to the 28 newtons, the perpendicular component to be 8.73 times 10 to the 28 newtons. In part 2, we calculate the initial velocity of the spaceship to be negative 4 times 10 to the 7 meters per second for the x component, 3 times 10 to the 6 meters per second for the y component, and 0 for the z component. In the computational model for part 1, we first describe the initial conditions, where we set the mass of the star to be 2.0 times 10 to the 30, and delta t to be 86,400, which is the number of seconds in a day. We describe the initial momentum by m times initial velocity, initial final momentum to be star times the mass of the star times the final velocity, delta v, which is the change in velocity, delta p, which is the change in momentum, and we set the net force equal to dp dt, which is the change in momentum over time. We calculate the parallel and the perpendicular components of the momentum, and we set the parallel component for the net force to be equal to the change in momentum in the parallel direction, and the perpendicular net force to be the change in momentum in the perpendicular direction. Then we calculate the mass of the black hole by modifying the gravitational force formula, where we multiply the overall force times r squared and divide by the mass of the star and the constant g. The code here is meant to depict the vectors and doesn't play a much greater role in the computation part. In part 2, we we set the mass of the black hole to be 1.221 times 10 to the 34. We don't change anything of the constants here, and we begin by defining the forces and acting on the planets and the objects at the time. The distance between the black hole and the planet is just taken by subtracting the position of the planet and from the black hole. We use the gravitational force formula to calculate the forces on the planet and the net force by summing the force of the black hole and the ship. Similarly, in the second part, we calculate the net force on the ship by summing up the force on the ship by the black hole and the force on the ship by the planet, where each force is calculated by the gravitational force formula. We use Newton's second law and the position update formula down below, where we update the velocity and the position by the formulas we listed below. In our overall discussion, we can say that even though the change in momentum over time and F net are mathematically equivalent, there is a difference in the way they are calculated. The rate of change in momentum can be calculated using the star's position, velocity, and momentum with respect to time. However, to calculate the net force, we must first know the black hole's mass beforehand. In the second part of the discussion, where we were asked to find the velocity so that the spaceship makes an orbit on the black hole, I tried doing that for a good bit. However, I even after like 30 or 40 minutes of messing around with the code, I still couldn't figure this out. Thank you.